Hello, everyone. My name is Stefan. I work as a contractor and consultant here in Berlin. And I help small and mid-sized companies around the world with LLVM-based tooling. We kickstart products, maintain toolchains, discuss ideas, train employees. And today, I want to talk about past plugins. In particular, the past, the present, and the future. And I don't want to spend too much time on the first two aspects and rather focus on number 3, where the core question is, should we extend that concept to allow for richer out-of-tree extensions in the future? That will involve some questions, and it would be great to collect your feedback and maybe also your ideas. So there will be a roundtable right after the talk. If you have anything to share, please come around, talk to us. And there will be another one tomorrow that I will announce at the board. Another note beforehand, the plugin term is quite convoluted in LLVM. I'm not talking about LTO plugins, and I'm not talking about Clang front-end plugins that work on the IST. I talk about pass plugins, and that's the ones that transform LLVM IR, and we usually pass them as -f pass plugin to Clang. If you want to know the future, look at the past is the phrase that I wanted to put on this slide originally, but then I couldn't hold back and use the quote from Fabricator. Don't dwell in the past, don't dream of the future, concentrate the mind on the present moment. Focus. That's a great quote. It's not from Fabricator originally, but it's a good match for a 404 page, and I guess I'm not the only one who remembers that. Can we have something like that on GitHub as well? I don't know. Anyway, in the past, we had legacy pass plugins, and they work with a legacy pass manager. And we used the -load option to DL open them, basically, and then each such plugin had a static initializer that takes the pass registry and adds its own passes. Poly was always the public reference implementation, I believe, and we see here how Poly did that. That is nice and simple, but it has two downsides. The pass registry had to be a global static instance, and plugins kind of sneaked in their passes without actual cooperation with the tools, and that causes all kinds of problems. So things changed with the new pass manager. Modern pass plugins, how I call them here, were introduced in 3 steps, basically, or 3 milestones that I linked here. And in summary, the most important change was that the control was inverted. So now the tools are in control, and they initiate the interaction. And furthermore, we have an example entry now. That is the by example, because it's called like that because it waves on each and every function that goes through the optimization pipeline. And it shows how to implement or how to register passes with the legacy pass manager and the new pass manager. On the plugin side, in modern pass plugins, we implement a defined interface like that, and it takes a callback with a pass builder reference. And then we return an instance of the struct from a well-defined entry point that is called LLVM get pass plugin info. And we see here the implementation in the by example. It takes the pass builder and just calls the same register callback functions that any entry tool would use. On the tool side, we just enumerate the plugins that we want to load, we DL open them and call this function with the actual instance of the pass builder. And that is great because the code paths don't differ between in-tree tooling and out-of-tree tooling. And we can use the same concept in MLIR, just with different prefix of the entry point. And we keep the existing benefits like the C interface for plugin registration and fast builds against LLVM release versions. But there's also one downside, or something that we did not improve. And that is that the pass base class is a C++ template class, and the pass builder is a C++ class as well, which means we pull in the C++ ABI into the static library interface. And That causes some issues. Mostly it makes plugins hard to build correctly. There's so many things that can break your API. We have to admit that most plugins use the C++ API anyway, because the C API is often not flexible enough. But, well, the compatibility issues are there, and we basically need one distinct plugin build for each compiler that we want to target on each platform in each SDK version. And that's, well, not optimal, it's possible, but, well, something we might want to think about in the future. If we had the IR dependency alone, we would need one plugin per platform and LLVM release. We're coming back to this a bit later. The tools that support our plugins are, well, opt, of course. We can even select a path to run there. This is great for debugging and development. Then we can use that -f path plugin option for Clang, Flang, and Clang REPL, which I wrote a blog post about last year. And then we have support for LLVM path plugins in Swift on mainline now. In Rust, there is an unstable option where we can use LLVM passes, but we have to enable this LLVM.plugins option in the build configuration of Rust, and this is a bit unfortunate. So the regular nightlies don't support LLVM passes. And surprisingly, LLD supports LLVM IR passes. For those that are surprised, this is for LTO-enabled builds, where the opt pipeline runs at link time. And it uses the new path manager, just like the compiler does. The plugins that we find in the wild are, well, Poly is in tree today. Then there's Ensume, which is an autodiff plugin that works on LLVM IR. And then there is the open source implementation of the OMVLL plugin from Build 38 that does native binary obfuscation. But that's about it. I know there's a few in-house projects that use plugins, but all in all, it is still kind of rare. And that makes the transition to the future, where the question is it that people are not interested in extending the compiler that way? Or is it maybe the interface that is too narrow and doesn't allow for good extensions? And here we come to the motivation part. So the claim is there is a larger demand for domain-specific compiler extensions than what we see today with path plugins. And that is probably because people find other ways to implement their needs. To get some evidence here, I think it makes sense to look at sanitizers. What we see here are the supported sanitizers in tree since release 4 in 2017. And it seems that the number is plateauing in the early 2020s. And that makes total sense because sanitizers used to be tools that help us live with the inconveniences of C and C++, like missing memory safety, undefined behavior, missing thread safety, things like that. And now that we filled all the gaps, we have all the sanitizers, and maybe the list is complete, right? Kind of makes sense. But then last year, the opposite happened. We got 3 new sanitizers added. How's that? Well, let's look at the newcomers. We have type sanitizer now that lets us check for type-based aliasing violations. We can check for floating point precision issues with the numerical stability sanitizer, and for blocking calls in code with deterministic runtime requirements with the RealtimeSanitizer. Well, type sanitizer is kind of C-ish, yes, but the other two are clearly cross-language concerns. And, well, this is always a point of view, and this is only my opinion, but I think they are at least a lot more domain-specific than the sanitizers that we had before. And this is the observation here. More domain-specific, less C, C++-specific. It might happen that now the list is complete and in the next 10 years we have no new sanitizers added. But if this is not the case and more proposals come up in the future, should we keep building everything, all of them upstream, and ship them to the whole world while just a tiny fraction of our users actually need them? Or should we maybe come up with an alternative and support rich out-of-tree extensions like sanitizers with some infrastructure? Could we implement that with a pass plugin today? Well, plugins used to be like narrow and do like static local transformations, so it doesn't seem like that. But let's see, what do sanitizers do? They need a front-end part where they have attributes to control where and how they apply or not apply. They have an IR pass that does instrumentation, adds shadow memory markers, calls into runtime library, things like that. And then they have a tiny driver addition that adds the runtime library on the link line. Well, the instrumentation pass we can clearly do with a plugin. But what about the others? Maybe let's see how one of the newcomers is implementing that and how we could maybe do it with a plugin. So I choose the RealtimeSanitizer here because I was in touch with the developers. Thank you very much for your feedback, RealtimeSanitizer developers here. And we look at the situation where we have RealtimeSanitizer built in compiler RT and LLVM. So in Clang, they added built-in attributes as well, which is blocking and non-blocking, and they translate into the LLVM versions. Sanitize real-time blocking, sanitize real-time. In Swift, they created a RT-san standalone Swift package that wraps the C API of the compiler RT header. That is interesting. They don't need the attributes because they have expression macros to express that marking of functions to say, here it should apply, here not, that is an exception, things like that. And the same is true in Rust. They have procedural macros to mark their functions. And they have a crate called RT-san standalone. They also prepare an RC to implement it built in Rust, which I don't want to comment further here. In my opinion, the modular package-based design is the perfect solution for these kinds of extensions. So how would it be if we did not have the RealtimeSanitizer built in LLVM? Then we wouldn't have the built-in attributes in Clang either. Well, but we could replace them with a front-end plugin in Clang that is allowed to define Clang attributes. Perfect. That could fill in the blocking, non-blocking attributes. Well, if we don't have anything built in to translate that into how can we replace the LLVM attributes then? Well, in principle, we could emit annotation attributes, and the IR pass would still be able to detect them. This is something that I would like to discuss on a roundtable. Can we use annotations here? Is that a proper solution or not? Or could we maybe even teach pass plugins to define LLVM attributes, just like Clang front-end plugins define Clang attributes? That would be the ideal solution. But any of the two would do, I think. And if that is the case, then we could combine our pass plugin with a front-end plugin in one shared library and just ship that. This is what, for example, Clad does, the autodiff plugin that works on the Clang AST. And in modern languages, I think, well, if we have language constructs that define what we do in Clang with attributes, then they could probably emit annotation attributes as well. Or at least we could give them an interface to do that. What's left is how to add the runtime library on the link line. Maybe some of the auto-linking features help that we have today in LLVM already. That's like named metadata entries that are listed here, LLVM linker options and LLVM dependent libraries. Well, yes, they are format specific and they require support from the linker. And it seems a bit abusive to just inject them from a LLVM IR pass. But on the other hand, it doesn't seem impossible to do that. So question for the roundtable, could we make that a bit more consistent maybe? Or does anyone have an even better idea how to do that? That would be great. Because if that was the case, then we could already implement sanitizer-like extensions out of tree, at least from a functional perspective. And I wondered, is there non-functional aspects here as well? And for that, I want to have a very short look at the story of the RealtimeSanitizer here. You can read the RFC on your own. I don't need to discuss all that, and look at the 150 PRs that went in tree since it landed. The most important thing here is that it started as a hack in LLVM, in a fork of LLVM. And if you start a project as a fork of LLVM, then it's very easy to imagine a future of your work to be upstreamed into LLVM. That is a natural evolution of your work. Most other forks, most other features don't survive downstream of LLVM, right? And from the developer's perspective, reusing the infrastructure from other sanitizers is one of the most important reasons to go for the upstream solution inside LLVM. So these are the aspects that my proposals tackle. If someone asked me what to do to promote out-of-tree extensions in LLVM, I would say that. Provide reusable infrastructure first, make it a playground for users to test their ideas second, and third, as a consequence, motivate vendors to support plugins and maybe even ship them. Looking at the first point, what we have today is a plugin interface with unit tests and one example in tree that has a lit test. But unfortunately, our bots don't build examples so much. And so the lit test almost never runs. And so the example has issues with many configurations of LLVM. And also, vendors don't ship examples so much. So if you want to test a plugin with an SDK, you don't have one. You have to build it from source, which is not easy because you have to match the C++ ABI of your compiler, and this is pretty complicated if you don't have a reference. So the point or the idea here would be, should we maybe make a reference plugin that builds and deploys by default? I think that would help a lot of people. And if we had such a plugin, maybe it had a bit more complexity than waving at functions, but more like a real-world thing, and it could support LLVM and MLIR maybe, and do something useful that people can experiment with. That would be great. Maybe even consider a pure C interface. And then, the idea is, why don't we make a plugin that loads a Python script and runs that as a pass in the pipeline? Python is super popular. It would make for a real-world extension. We could even show how to link libPython statically if we don't want to go with a dynamic dependency. We have more than enough bindings for LLVM and MLIR. And it seems to be nice because you could write IR transformations without rebuilding the plugin. Imagine a world where you can download your compiler from apt and also install the plugin right away with it and just tinker with a Python script to try out and tinker with pass transformations. That would be possible if we had that as a reference plugin. And by incident, actually, there are 2 open source repos with a proof of concept, and only one is from me. The first one I did last year as a bit of research for the OMBLL project, and the second one just popped up at the same time. It's written in Rust, and I never met that person who wrote it, but it's a funny incident. So last but not least, we should try to convince vendors to support and ship plugins. And for that, maybe we have to take their concerns seriously. There are markets where it doesn't sound like a good idea to have arbitrary plugins flying around that tinker with your internal code, because they might introduce vulnerabilities, and that is a security issue, and that is fair. So we should give vendors a way to control that, and why not do that by code signing? A plugin would only be loaded by the tool if it has a proper signing, and then vendors could say on our platform, we want to audit the plugins that are allowed. That would be totally possible and totally fair and reasonable to me. And for Rust, which has a bit of a problem with C++, we could maybe wrap the pass registration in the C interface. and have the reference plugin as a pure C interface plugin, because plugin registration is C already, and Python bindings use the C interface as well. So we're almost there, and that would be an interesting addition as well. With that, we're coming back to the initial Fabricator quote, because I think it's quite healthy to dream a bit of the future sometimes. And that's what we also want to do on a roundtable. So I invite everybody to come around and join. With that, I would say thank you very much. Thanks for your attention. See you later, and looking forward to your questions now.
So great talk. One question, or not really a question, but I could imagine for a lot of the sanitizers, you would essentially need not just pass integration into the LLVM IR pipeline, but also for the machine IR pipeline. Do you have any thoughts on that, on where problems there might be, or what would have to be done to kind of address that?
That is interesting, yeah. That's an interesting note, because right now, plugins only work for IR level passes, not for machine passes. And that is because the new pass manager does not expose the functions for that. I think we should teach the pass manager to expose functions to register machine passes as well, and then plugins would do that naturally. Like we don't have to add anything to the interface. We just need to let the new pass manager expose these functions. I think that would be a useful addition, yes.
Thank you.
Thank you for the talk. So what is the status for Windows support?
Windows support is interesting. There is a ongoing effort to allow to build the LLVM shared library on Windows. The problem there is that we had too many exported symbols, and Windows only allows like 64K or something like that. And there is an ongoing effort to specify which symbols are exposed so that we can finally build the LLVM shared library as a DLL. I think this is like 75% through, and if this is done, then we can also support plugins on Windows.
Thank you.
Thank you. No further questions? Then thank you very much for attention, and see you at the roundtable, hopefully.